Hello, legends. This is Mr. Mays coming to you through the iPad, through the metaverse, through the magic to talk to you a little bit about binomials part 2. So this is still our same old our same old binomials. But this is part 2 for our binomial distribution. Get rid of the S, actually. I want it to be distributions. And for binomial distributions part 2, we're going to do the structure a little differently. Now, you should go through the slideshows that are available on Canvas, but I just want to walk you through one particular problem. I want you to pull up the classwork 4.5 to be exact. And we're going to take a look at just the problem that's called part 1. And it's the one about children with type O blood. It says each child of a particular pair of parents has a probability of 0.25. And you'll notice there's an A and a B to that, followed by 6 questions. And we're going to go over those 6 questions today and use those 6 questions as a way of determining the things that we need to know about binomial distributions from part 2 of our studies. Okay, so before we even dive into that, you should have it dragged up beside you, okay, beginning with question 1, which says complete the probability distribution for the number of children that will have type O blood. But what I want to do, above all else, is I want to make it clear what we're going to go through, okay? So today we're gonna practice different probability of X in relation to K calculations. Okay, so what I mean by that is, what are the odds that at most this many successes occur? What are the odds that more than this many successes occur? Less than this many successes occur? There are a lot of signs that we mess with. Everything from less than to greater than to less than or equal to greater than or equal to even equal. And we're going to look at how each of these show up in problems. I'm going to show you how to solve them using this example problem. That's thing 1 you need to know how to do. And thing 2 you need to know how to do. I should probably enumerate these. Thing 2 you need to know how to do is you need to know how to find the mean of a binomial distribution and the standard deviation of a binomial distribution. Let me show you those equations mad quick so we're all on the same page. The way you find the mean of a binomial distribution is fairly straightforward, thankfully. I mean, we don't want complications. That we don't want. It's just the number of total trials multiplied by the probability itself. And this is actually the mean that you're most used to, right? It's the mean that you would have answered had you not been in this class. Had you never decided to study the wonders of applied statistics at the college level, you still would know, if 20% of people are hanging out and there are, 30 people that I'm pulling from, I would take 20% of 30, and lo and behold, I would have 6 people as my sample, right? And that would be expected, right? We would do number of trials times the probability. Now, the standard deviation's a little bit uglier, but that said, it will still be solvable and functional. It is the square root, because we are finding the variance and then finding the root of that variance, of the number of trials times the probability of success times the probability of failure, which is 1 minus the probability of success. So let me mark that out for us. This is number of trials. This is the probability of success. And this is the probability of failure. And then we've square rooted it. And what this is saying, if you remember how we've done in previous parts of this same unit, how we've done standard deviation, we find the variance and we take the square root. And we often find the variance in situations where we are adding together different distributions. Well, what you'll notice here is we're essentially multiplying the odds of success times the odds of failure. That'll create the amount of dissonance, the amount of unsurety in our equation. And then we'll multiply it by the number of times we're doing it, right? So the number of times we do the distribution is the number of times we have success and failure interact. Okay, so these are the big 2 things that we're doing today. And now we're just going to test them out together to make sure you understand them, and then you're going to apply them. So for 4.6, Part 1. Question 1, completing the probability distribution. I want you to take a look. The entire probability distribution is sussed out in the in the slideshow, but let me just walk you through really quickly what we would do. You would do binomial PDF for each one of the projected outcomes. And those outcomes are, right? 0, 1, 2, 3, 4, and 5. Right? Because there are only 5 possible children. You can't have 6 with type O blood because, of course, there are only 5 children. And you can't have less than 0. You can't have negative children. It's just not an option, right? And we will do binomial PDF where our trials total is 5. Our probability is 0.25 because that's what the question has told us. There's a 0.25 chance of having type O blood. And we will try each one. We'll do success as being 0, as being 1, as being 2, as being 3, as being 4, and as being 5. Altogether, this will add up to a total distribution, right? Where the top is x, and this is p of x. And so lo and behold, we plug our values in, and I'm getting the following. You should compare yours against mine. For 0, I'm getting like 0.24, 0.237. For 1, I'm getting 0.396 about. For 2, I'm getting 0.26. For 3, I'm getting 0.088, somewhere in that area. For 4, I'm getting 0.015-ish. And for 5, I'm getting 0.00097. So we'll do 001. Okay, just rounding up here. This doesn't exactly add up to one whole, but it adds pretty close, so we'll roll with that. Okay, that's for question 1 of part 1. Okay, let's move on to question 2. And that should make sense. This is effectively you drilling and practicing binomial PDF for the specific individual values under the curve. So effectively what I showed you in your notes was if you're looking at a distribution, a binomial distribution, the peak is your probability of x. And if you pick a particular value, what you are essentially doing is you're saying, let's say I pick 0, I look at the spot where 0 exists, and I'm saying I just want the probability that sits under that discrete value. Because remember, there's 0, then there's 1, then 2. Each one of those values has a discrete branch of the undercover value, right? And so that will be the thing that I'm calculating with binomial PDF. And we just did that for the entire curve. Okay, moving on to question 2. Let's do part 2 in green. What is the expected number of children? Expected number. When you see expected number, you know that that is the mean. Well, what do we do? For the mean, of course, we do number of trials times the probability. So there are 5 trials, and the probability is 0.25. This one, wonderfully so, should feel easy. Should feel like a joy, a smile. And you should get 1.25. So on average, 1.25 children out of 5 have type O blood. Check-a-rooney. Let's look at question 3. This one I'm going to keep in green because it's a similar question. It says, what is the expected number of children that have type O blood? But part 2, oh my goodness, wait a minute. No, this is part 2 of question 2. What a fool I am. I found my expected value. I now must find the standard deviation. Standard deviation in this case is equal to, as we said, the square root of the number of total trials times the probability of success times the probability of failure. So when you do this calculation, you should be getting 5 times success is 0.25 times 1 minus success, which is 0.75 failure. And when you run that entire calculation, I get 0.9682. And that is my standard deviation. We've done it, legends. Oh, I'm so proud of us. Look at that. We have our mean and our standard deviation for what before was simply a binomial distribution. We have now learned how to find specific values, right, which we should already know about binomial distributions. But now we know how to run all these calculations on binomial distributions. Just like with normal distributions. We now have the standard deviation and the mean, aka the expected value. All right, let's move over to part 3. This is where things get spicy, as they say. Find the probability that no more than 3 of the children have type O blood. First, I'm going to put the nomenclature. No more than 3. So x, that value, no more than 3. So less than or equal to 3. It says no more than 3, so that involves 3, and it is less than 3. So this is how I would say no more than a number. No more than a number. And what that looks like on a curve, I just want to sketch it out. If this is my binomial curve, this is 0, 1, 2, and 3, and then the remaining numbers. No more than 3 means we shade everything including 3 before 3. And you should already know with your brilliant minds that in order to do that, no more than 3, all you got to do is binom CDF. Remember, C is cumulative. So instead of giving you just the point, 3, that we get to, binom CDF gives you 3 and before. Or I should say from the first value all the way up to 3 under the curve. So when you go into binom CDF, you'll do trials, 5 of course. Probability of success, 0.25, the same as it was before. And in this case, we will put our x value as 3. That includes 3. That is so important that you know that binom CDF includes the value you're using. The value I'm getting for this one, okay, is equal to 0.9844. That should be what you got. And now we're going to move on forward to question 4. It says, what is the probability that less than 2? Again, you should get your thinking pants on, so to speak. All right? Less than 2. Probability that x is less than 2. Pause the video and see if you can figure out how this one should be solved. And thank you for coming back. Probability that less than 2 have it. Well, if I'm thinking on my distribution, right? 2, less than 2 is everything before 2, but not including 2. Does that make sense? We're not going to include 2. So really, it's everything up to 1, because these are discrete values. So I already know what I'm going to do. If I want the probability that less than 2 of the children have type O blood, I'm going to do binom CDF. Trials the same, will be 5. Probability of success, the same, 0.25. But my x, I'm not going to go up to 3. And I'm not going to go up to 2, because it doesn't include 2. I'm going to go only up to 1. Cumulatively, I'm essentially adding together probability of 0 and probability of 1, right? Because less than 2 would be only those 2 values. And what I'm getting when I add those together, or when I run this binomial function, is the probability of x being less than 2 coming out to 0.6328. Beautiful. Okay, you should be feeling like $1,000,000. We only have 2 more practice problems to go, and you will know your stuff inside out and backwards. You should then go through the remaining problems, try them out, suss out the solutions, and feel very, very confident in binomial distributions. That's it. That's all we have under our tool belt. So let's take a look at number 5. Let's do yellow for 5. Oh, I wrote 6, not 5. Mr. Mays, where's your head today? Lost, good sir, or madam, or person. Find the probability that more than 3, this is important, probability x is greater than 3, that more than 3 children have type O blood. Okay. Again, I think about my distribution. I think about 3. We want the probability that more than 3, but not including 3. 3 is not included. Okay, I only want above 3. Now, my binom CDF function is obviously what I'm going to use. But I have to be aware, I can't do a right-tailed test. I can only do a left-tailed test with binom CDF. That's going from the left to the right. Okay? In that instance, I want all the values that don't include 3 that come before it, and then I'm just going to subtract that from 1. So I'm going to take this whole side and subtract it from 1. I'm going to call that a number, right? That number, I'm going to subtract that number from 1. Okay? So I'm going to do binom CDF. I'm going to do trials, the very same, 5. Probability of success remains the same, 0.25. And I'm going to do x going all the way up to 2. Not 3, because I don't want to include 3 in this particular structure. It says probability of more than 3. Oh, wait a minute. No. I'm incorrect. I am thoroughly incorrect. I do want to include 3. Hopefully you're shouting at the screen. Mr. Mays, of course you want to include 3. You don't want to include 3 because of your, in the right side, which is what you eventually want to end up with. But you do want to include 3 on your left side, because that's what you're removing from the total whole of 1. So I am going to go all the way up to 3, right? The probability that more than 3 have type O blood. I will find the probability that 3 or fewer have type O blood, and then subtract that from the whole. And when I do that, when I do 1 minus the value I get from this, from binom CDF, I end up with the lovely answer that I've been waiting for this whole time, which is 0.0156, right? And that is the cumulative value that I get from adding probability of 4 and probability of 5 together, because those are the only 2 values that I have sitting there. You could also do those 2 probabilities together and add them together. This is just easier, especially when we have more probabilities to mess with. That should make good sense. And then finally, let's do purple. My favorite color. Not really. Orange is my favorite color, but purple's a solid second. We'll do number 6. And that says the probability that at least 2. Okay, so at least 2. What does that mean? Well, that means probability of x being greater than or equal to 2. At least 2. So on my curve, if this is 2, we include 2 because it's at least 2. So it's everything above 2 and including 2 that I want. Now, again, this is one of those reverse ones where I want a right tail thing, but I only can find the left tail. So this is going to be a 1 minus. Okay, I know that. I'm going to do binom CDF because we're heroes. We love it. This is our 3rd time using binom CDF. We're going to do trials 5. We're going to do probability 0.25. And for x, we want to include 2 in our final value, but that means for our subtraction, we don't want to include 2. We only want to do cumulative up to 1, and we want to do 1 minus the value we get from this. And that should yield for you 0.3672 approximately. Okay, go through these, separately look at them and make sure they make sense to you, okay? And then be sure to go through the slideshow and go through the cheat sheet of all the different greater than or equal to, less than or equal to, greater than, and all that, and the different binom, CDF, and PDF functions that we use to find those, okay? If you know how to do all this, alongside finding the mean and the standard deviation, you know everything you need to know about binom CDF. The last thing I want to warn you about is sometimes they'll give you a percentage, and you'll see this in the later one, this chickenpox question that happens in part 2. Sometimes it'll be like the odds of having chickenpox is 90%, so it's 0.9. What are the odds of not having chickenpox? In that case, you have to do 1 minus the probability. Not is 1 minus the probability, and then you use that new probability in place. Okay, we have learned all of the ways in which we can calculate different functions of the binomial distribution using binom CDF and binom PDF. We've learned how to make the entire distribution setup for a binomial distribution. We found the expected values and the standard deviations of binomial distributions. And lo and behold, we have become masters. Stay tuned for next video where we go in depth on geometric distributions. You are my heroes and my legends. I am so proud of you. Practice, practice, practice. Drill all of the classwork, all of the homework. Look greatly forward to future lessons. Thank you for being a part of my class. This is Mr. Mays signing off.